Hello student, to the second class of our course wave optics, where we're going to introduce the brief concept of quantum optics that we mentioned in the first lecture so far. So let me go directly. Okay. So in the previous lecture, I mentioned that the optics can be understood in three basic approach. One is ray approach, we called ray optics. Another is wave approach, considering light to be a wave, we call wave optics, which is our course in fact. And another is quantum optics. We already discussed how the ray optics and wave optics picture one can schematically show when the light source emits the light. However, quantum optics is also a very upcoming field, or the most modern approach, where one can introduce the light as a quantum particle. So that we already know. So in quantum optics, what happened? The propagation of light is described by, or described in terms of, or described by a large number of tiny particle like packets of optical energy. So packet of optical energy is like the light can be described, the propagation of the light can be described by the large number of tiny particle like packets of optical energy, and these particle like packets of optical energy in general called photons. So this wave packet, this photon is generally called wave packet. The energy of wave packet, if I calculate E, that is the energy of photon, depends on the frequency of this light, and it is simply written by E equal to IGNOU, or hc divided by lambda, where c is the velocity of light, lambda is the wavelength, and h is Planck constant, whose value is around 6.626 into 10 to the power of minus 34 joule second. This is Planck constant. Lambda is a wavelength of the light, and c is a velocity. So the energy of the photon, one single photon or wave packet, can be described by this. Now, in the similar way that we had done in the previous few cases, that how the normal source will emit light in terms of these wave packet, then the schematic picture will be like this. So if I have it, say, torch, again a very well known light source. So instead of having, in the ray optics we have ray, in the wave optics we find that it emits light in the form of wave, but here what happened, it will emit light in terms of photons. So the picture will be something like this, like bunch of photons is emitting from so this bunch of photons are emitting. In a similar way, if I have a laser source, so it will also emit bunch of photons like this. This is a very schematic, a very simple schematic figure to understand the different approach of the light. And similarly for the sun, it will emit the light in all the directions. Okay. So in quantum in quantum optics, this light matter interaction is very important. So what is the meaning of that? So suppose we have a medium, and when the light is falling here over this medium, it will interact the atom inside the medium. That is the basic thing that we have. And then from the medium, light will going to scatter, or there should be an absorption, or something is emitting. But the important thing lies here, and that is light matter interaction. So there are different model that we have to understand how the light will going to interact with the medium. And if I write here the model, say this is the model, it can be classical, it can be semi-classical, or it can be quantum. So suppose I make a chart like this is the model we describe, through which we describe the light, the interaction of the light with the material, and this is the atom we have, nature of the atom, how we define the atom, and here how the nature of the light if I write. Then in model 1, which is the basic classical model that we are going to discuss in this course, then the atoms are merely considered to be like a oscillator. These atoms behave like a are like classical oscillator. Okay, the atom behave like a classical oscillator, and light also consider as a classical electromagnetic wave. So atom is also considered as a classical object and light is also considered as a classical object. So the model is classical. There are another model also, semi-classical model. In the semi-classical model, atoms are no longer considered as this oscillator. Rather, if I write in a schematic way, if I draw, it is quantized. The atom can goes one level to another level in a quantized manner. Quantized states are there. So atoms are considered as quantized. However, light is still considered here as a classical electromagnetic wave. In the third approach, which is basically a quantum mechanical approach, it is a quantum mechanical model or quantum optics. Here, both atom and the light both are quantized. So atom is quantized and also light is no longer considered as electromagnetic wave, rather they are considered as quantized particle. This quantized. So very roughly I try to describe different models, and here we are describing the quantum optics, why the quantum optics is important, that we are going to understand soon. So here three different model we describe or just make a chart, and one is a classical model where the light, when it is interacting with the material which is made of atoms, we also consider as a classical oscillator, so as the light that is incident on this kind of material, they are also considered as a classical electromagnetic wave. But in quantum approach, both atom and the light both are considered to be quantized in nature. Now we know that for quantum optics, the light is considered as a photon, and if I calculate the energy of a single photon with certain wavelength, for given wavelength, then we will going to get some number, and that number decides few things. For example, this is the expression of the energy of a single photon. Now if we have lambda, say 600 nanometer, then the energy of the photon, if I calculate, it should be 6.6 roughly into 10 to the power of minus 34, and then 3 into 10 to the power 8 meter per second, that is the value of the C, divided by 600 into 10 to the power of minus 9. So that quantity will be in joule, and if somebody calculate that, this value will be roughly around 3.3 into 10 to the power of say minus 19 joule. So the energy of a single photon is of the order of 10 to the power minus 19, which is extremely small. This is a extremely small quantity, right? Now that means if 10 to the power 19 photons, this is the number of photon that hits a photodetector, per second, ten to the power 19 photons hit the photodetector per second, then it will give 3.3 watt. So the number of photons, so that is normally the value in the normal life we deal with, 10 to the power 3.3 watt or some watt level of energy, light energy. So that means in order to have this light energy which we use in our daily life, number of photon that is associated with that is of the order of 10 to the power 19, which is very, very large. However, if we want to study the nature of the light in photon level with 1 or 2 photon, then the amount of energy will reduce radically. Then very, very small amount of energy we need to deal with. But in normal life, we don't have that much of precision. We don't have those kind of instrument in a normal life, in a regular life, to detect the light in that order. So that's why precision is something for which it basically decide whether we need to go to a quantum level, quantum optics level, or a ray optics and wave optics is sufficient to understand different light phenomena. So that's why the wave optics and ray optics are normally used to understand the light, the nature of the light in daily life, rather going to this understanding the very precise nature of the light, the quantum nature of the light, where we need to deal with the photon, 1 or 2 photon. There are instruments available in the market where you can have there are photodetectors, we can detect even 1 or 2 photons, but that is not required in daily life, because in daily life we deal with the number of photons of the order of 10 to the power 19 that we just do. So ray optics and wave optics is sufficient. So what the ray optics will serve, so let me write. The ray optics basically, the ray optics covers the topic like reflection, then diffraction, then dispersion, this kind of phenomena. This kind of phenomena very nicely described by simple ray optics approach. On the other hand, wave optics can cover phenomena like interference, then diffraction of light, and polarization. So in our topic, we are going to discuss all these 3 phenomena. This is in our present course. These are the 3 phenomena that we are going to discuss under wave optics. So with this small discussion from the previous class to this class, we try to understand that different approaches are there to understand the nature of the light. Ray optics is used to describe certain phenomena. Wave optics is used to describe certain phenomena of light. And finally, quantum optics, which is the most modern approach to understand the phenomena of light, different phenomena of light, is used for understanding certain phenomena based on the quantum level, where the number of photon is less. Well, with this note, I like to go to our main topic, which is wave optics, and we essentially start our topic today with something called wave propagation. So far we are discussing about the wave optics, and several times we mention about wave and all these things. So now we are going to quantify what is wave propagation, we quantify what is the wave equation and its solution, etc. in detail. So wave propagation, that is the first thing we are going to understand. Before going to typical wave optics, first we need to know what is wave and how it propagates. Wave propagation. So in wave propagation, what we have, let us first draw a coordinate system. Suppose we have a coordinate system O prime, and in this coordinate system I have a wave. Maybe I can put the wave in a different color, a disturbance or a wave like this. This is the point of some point on the wave. Okay. Now this function I can write as, this disturbance I write as a functional form like y fx, and this is my x prime coordinate and this is my y prime coordinate, and we call this as stationary wave because this wave is not moving. Stationary wave. Well, if the wave start moving, and this is my stationary frame, actually fixed frame. Now suppose the wave is moving and it goes to some other point here in this location. Then the coordinate associated to this fixed wave, if I draw that, it is also moving with certain velocity, and that is my old O prime frame. And here, this point, whatever is marked here, I marked here once again, is my, say, suppose that was my x prime point previously. So now this point with O reference frame, which is here fixed, is x. But from here to here, it was x prime, and this value is with respect to O prime frame. So from here to here, this point, it is x prime. And if the velocity of the wave is v, then from here to here, this length should be vt if I consider the wave at some time t. Okay, so this figure is when the wave is traveling. So this is for stationary wave and this is for traveling wave. But the point is, I can have the coordinate x like x prime plus vt. So here x from here to here, this length is this length plus this length. Or in other way, x prime coordinate is simply x minus vt. So y, which is same here because the structure of these waves is not changing. So here also I can write this disturbance as y in the O frame, which is equal to y prime, that is f of x prime because it is not changing its shape, and x prime I now have x minus vt. So this is x minus vt. So if this wave moves in opposite direction, I can also have, then this sign can be a plus. So we have in general for a moving wave, y is equal to f x plus minus vt. Okay. Now with this note, we can also write something that if that is the case, then all the waves or all the functional form having these specific argument can behave like a wave. So if I write, okay, before that let me write something. So x equal to x prime at t equal to 0, that is the original shape we have. The original shape that we have of the wave, the original shape of the wave, that was y prime is equal to f of x prime. Does not vary, as I mentioned, does not vary, but simply travel along x direction. So that means initially I have a wave here, and after some time this wave moves here. If this is my one coordinate system O, so it is now here, this moving coordinate system, it is not moving at all, but there is a relationship between these two coordinate system, and this relationship is x prime is equal to x minus vt in this case, where v is the velocity of the wave or the velocity of the reference frame that is moving. Now if I write y equal to a, say, sine some constant k x minus vt, that is one functional form we have. Now I am putting some functional form. I can also have different kind of functional form, write simply a x plus vt square of that, or we can have function like e to the power of k x minus vt and so on. The point is, in all the cases, the argument of this function is x minus vt or x plus vt or x minus vt, or in general x plus minus vt. Whenever you have the two coordinate system associated with each other like x plus minus vt, then that particular function is always represent a propagating wave. So all this function here, all these functions represent a traveling wave. So in general, if we have a function like psi equal to if some constant c1 if x minus vt plus c2 g x plus vt. So this essentially a general form of a function that expresses a wave that is moving along x direction, positive x direction with velocity v. If the sign is plus like this, then it means that the wave is moving in an opposite direction. In this case, it is moving from this direction to this direction, right, from left to right. If the wave is moving from right to left, then the sign will be plus. So today we find a very important thing, that if a function has its argument in the form of x plus minus vt, where x is a coordinate along which the disturbance is moving and v is the velocity, and if I manage to write the function in the form like x plus or x minus vt, then that particular function always represent a traveling wave. In the next class, we will show that if we have a functional form like this, it should follow a sudden equation, a sudden differential equation, and that differential equation is called the wave equation. So we will formulate the wave equation in the next class and show that this particular form is a general solution. For example, psi here is a general solution of the wave equation. And with that, we are going to understand, in the previous class, we write the electromagnetic wave in a very specific mathematical form. Why we write this mathematical form in that specific form, we are going to understand. We are going to then understand that why we have written that particular form after having an idea about the wave equation.